Thank you very much. It sounds like I'm very old, but I'm not. My age is not much different from the Barkov. Sorry then. But anyway, my talk is a bit different from the other speakers. So every unloading story begins from this figure. PVA and MVO2 relationship, and the PVA gets larger, oxygen consumption becomes larger with significant offset, which is independent of PVA, which is very important. And if the heart rate increases, we know that for same PVA, oxygen consumption is higher. So if we can manipulate this PVA, we can manipulate the oxygen consumption for sure. That simple idea is introduced in Impella business. And this is our data, so this is partial support, total support. In that case, partial means the heart remains ejecting under Impella support. Total is no longer the heart no longer ejects, and oxygen consumption reduces. As PVA reduces, consumption reduces. A month later, we compared infarction size, and there are really major impacts on the infarction size. So it works. However, this concept is, in some way, it's very simple, but for some people, it's very difficult to capture. So the education and training is a major driving source to promote Impella treatment for every patient. But I also understand it's not so easy to really practice in real medicine. And I'll show you why it's so difficult. We just increase this Impella flow. Let's look at this left ventricular pressure. Impella flow is increasing, pressure may not be changing, indicating that Impella is supporting some output, but the real output is not changing much. Left ventricular pressure does not change. So the easiest way of seeing this one is if we plot left ventricular pressure as a function of Impella flow, it becomes something like this. Up to a certain point, the increasing Impella flow does not necessarily decrease left ventricular pressure. Beyond this point, which is the point where total support begins, the heart stops ejecting now. Then the left ventricular pressure drops. The arterial pressure is higher than this, but this drop is very steep. Indeed, this is less than 5,000 RPM. Now, this span is about 100 millimeter mercury, so 100 millimeter mercury by 5,000 RPM means that to change 1 millimeter of left ventricular pressure, we have to change Impella 50 RPM. For this kind of device, 50 RPM is very small change. So this gives us basically two problems. One problem is how we choose a target unloading level. This is very steep. This is actually the line I transcribed from here to here. It's very steep. So how we choose a particular point of target value. The second one is how to keep that level by maybe manual adjustment, whatever it is, how to keep it. So we would like to overcome that problem. The first point I'd like to address is how to choose a particular spot. So again, PV loop. So idea is very simple. Maybe too simple to accept, but just let's accept. This is PV loop. Then we reduce left ventricular volume by Impella. So this blue part is Impella recruited left ventricular PVA. This yellow part is residual PVA. But depending upon this alpha level, this point is alpha 1, this point is alpha sum. This total PVA is now getting smaller and smaller. Now, in the right-hand side, this is alpha axis. we normalize by the end systolic pressure. Alpha 1 means that unloading level is just this level. If we lower the unloading level, the area gets smaller and smaller. So if we plot the relationship of this recruited area against total PV area as a function of left ventricular systolic pressure, we can get this kind of curve. So the point I'd like to make clear is that if we can lower the LV pressure, something like 40% of end systolic pressure, this is the point where the total support begins. If end systolic pressure is just like the 40% of this level, then if you look at here, we can unload almost 90% of PV area, 90%, only 10% left, which is pretty large. Even if we could go to zero level, as I explained already that there is a PVA independent oxygen consumption, which is almost 50% of total oxygen consumption. So this 10% may not play so much role. That's one point. The second point is how to keep this particular level of oxygen consumption. And this is a little bit complicated, so I'm not going to explain this. Basic idea is we introduced feedback mechanism to achieve that goal. The first step is we identify the target model, plant, that is to be controlled. And target is Impella LV combined system. This is target. Then we activate this system by changing Impella flow and measure change in left ventricular pressure under total support. So this is an experiment. We are imposing white noise perturbation. This is very efficient to characterize the system property. This is pump command signal, and left ventricular pressure is somewhere here. So from those response, we can characterize system and we can model the system with reduced order, something like this, very simple model. Once this model is identified, we can design the feedback regulator. And that is not a big problem. We can do it very easily. So we designed the controller so that the system gain changed over 20 times. So I guess that as long as people are living, that is beyond the required range of the variability. So then what we can get by this? This is the performance of the system. We change the command signal, like a 40 millimeter of mercury of left ventricular pressure, defined by this target value. Actual left ventricular pressure is here. This is the top, this is the bottom, so it may be difficult to see, but as soon as the system activated, the left ventricular pressure dropped to 40 immediately, then 70, 40, whatever level it is very easy to achieve, very simple. So this is just changing command signal, but what happened in changing the preload, maybe heart rate? Is this good enough to keep constant value of left ventricular systolic pressure? This is a volume perturbation here, heart rate perturbation, depending on volume, 8 plus 8 ml or volume minus 8 ml, heart rate double from here to here. Then it changes LV systolic pressure and PVA for sure, if support level is fixed, constant. But if we activate our system, this is what you get. Again, this is our command signal is LVSP of 40, so it's keep 40, 40, 40, 40. This is PVA, it's not 40, some value, but this is 40. So it works under those experimental conditions. So we immediately apply this technique to the ischemic unloading. That's the major theme of this meeting. So the protocol is very simple. Ischemia, reperfusion. About an hour later, we started this AIMUS, this smart Impella. Then a month later, we estimated infarction size. Very simple experiment. So a month later, end-systolic elastance is much, much higher. EDP is lower. Again, this infarction size is much smaller than untreated group. This is automated system. So I think it is working very well, and it's not optimized yet. But I think we can demonstrate the potential of this device. So after this, we have not done real experiment, but we are thinking of potential application of this technique. One application beyond LV unloading is manipulation of heart rate. As Dan Barkov said that we can change heart rate a lot. Now, heart rate intervention alone can reduce infarction size a lot. So if we combine this with mechanical unloading, the effect may be larger. The data I'm going to show you is not generated by the smart Impella system, but I think idea is the same. So if you look at only this part, it is very clear that for any given ventricular assist support level, whether the vagal nerve stimulation plus or minus, the heart rate is different. So the lower the heart rate, the infarction size is much smaller a month later. So we can control the vagal system by electrode. We are now developing a very simple electrode that may be applicable in clinical settings. So we combine that, we can feedback control vagal nerve activation, then therefore a heart rate. Then we combine that with smart Impella, we can achieve this in patient. Now the next thing I just briefly touch upon is that ECPella. We just had discussion on ECMO, and in Japan, somehow 40% of patients who are referred to Impella approved institution with ECMO already. So this is our initial condition. ECMO is there. Then we have to implant Impella. So the protocol is like that. By implanting Impella, I think because the perfusion pressure increases, this is animal experiment, so the PV loop gets larger. And by activating ECMO, depending upon the flow rate, high Impella and ECMO reduces PV a lot. So in terms of the PVA, something like this. But a month later, we are estimating infarction size. This is ECPella by far performed much better than ECMO for sure. So I will stop here, but the conclusion is very simple. ECMO, intelligent ECMO or smart ECMO, is capable of autopiloting LV unloading and reducing infarction size. And the smart Impella provides a higher standard of LV unloading everywhere, maybe anywhere. And so far, our major driving force to promote Impella was education. That is really true, essential. But computerized system, I think, complementary to improve the quality of care in medicine. And this smart Impella will open up the new era beyond simple unloading, such as Impella, combined with heart rate modulation, pharmacological intervention, ECPella, and probably BiPella. Everything can be controlled. Promotion of smart Impella or AIMUS not only benefit the patient, I think at the end, that's unloads cardiologist. Thank you very much.
Kenji, thank you. I particularly like your last statement there. The model that you've shown, although you've shown that it responds to changes in volume, at least initially, the left atrial pressure was pretty low, about 12 millimeters of mercury. Have you seen it function in a similar manner if your left atrial pressure is 25 when you put the device in?
Well, if we look at each data, I think we must have such cases, but I have only pooled data at this moment, so I can't talk about individual cases. Mm-hmm. But judging from the mechanism we are using, it should work to a certain extent.
Very good.
Yeah.
Dan?
Thank you, Kenji. I just wanted to understand a little better. Your choice in left ventricular pressure as a surrogate for unloading is challenging because as you volume unload, you can generate a very normal pressure because the chamber is, of course, smaller and the wall thickens further. So you could get an erroneous impression of unloading just because the left ventricular pressure is high. Am I missing something?
Well, the left ventricular pressure is high.
Could be high at a very small residual volume because you have a much smaller chamber and you can generate pressure because its fluid is incompressible. So then if your left ventricular systolic pressure is a target for optimization, it would seem it would be not a very good surrogate. Or is that, do you understand what I'm actually asking?
I'm not so sure, but this is based on the linear end systolic pressure volume relationship. So in that condition, once you lower the left ventricular volume, end systolic pressure must decrease.
But what you showed that with Impella, you can go a long range in increasing the RPM, and there's only this kind of a break point where the slope, meaning the left ventricular pressure, is going down at a very extended range of increasing the Impella RPM.
That's right.
So that will suggest to me that the reason you don't see it is because the pressure is continuously being, in a sense, regenerated in a small compartment, and therefore it gives you a sense that the pressure is high, even though the volume is unloaded.
Yeah, I think I understand the question or the comment, but I think that you're ignoring. Kenji kind of got to the bottom line, which is what you're saying is not possible with a linear and systolic pressure volume relationship. So when you're in this range of partial support, as you increase from low to high speed, what you're doing is transferring the flow from the heart to the device, and the ventricular pressure is really not changing very much until you get to the point where the aortic valve closes. And then at that point, as you increase speed, now you're working on the descending limb or the descending part of the pressure volume relationship. So I think that's the point, but I think the way you set up the question, I think, is not physiologically possible.
Right. But the preservation of the pressure is in the isolumic portion, as we just said. And that pressure can remain high. It remains high even in cardiopulmonary bypass when you do that. And it gives you the sense that the ventricle is not unloaded. But we'll take it out.
Okay. Yeah, so we will continue with following the discussion. Maybe Naveen, last comment, I think. Dan?
Oh, you go first.
So I was just asking Kenji, I thought it was really interesting about the partial and full unloading. So do you think that this concept of creating a smart pump and having longer periods of sustained unloading is superior, or do you think that having the myocardium work and then rest and then work and then rest is better?
So could you rephrase your question again?
So
what
compared
was
to
your
just
point?
complete, this is something that has been asked in many different forums, but in the acute MI setting, with unloading, do you favor complete continuous unloading, or do you think that this idea of intermittently loading and unloading is superior, the modulation approach?
In our case, because of our past experience, we applied continuous unloading. We are not applying intermittent unloading. But the duration of unloading is up to 3 hours. Then a month later, we evaluate the infarction size. That's our standard protocol. So during the unloading, it's continuous. So there is no, we can't really compare which is better, intermittent or continuous. So we don't have no data yet.
Dan?
So, so Kenji, there are two important things that resonated from your talk. One is the piece about education, and I've been spending a lot of time with educating, and it really is, I think, has been really critical once kind of a light bulb goes off, when people understand what is unloading and how do you describe it, and it really helps to. It has really helped a huge amount for people to understand the difference between Impella and ECMO, and also why the combination works. And without this kind of really just very simple, it's not getting very, very deep. So that really resonates really, really strongly with me and my experience. And the other point was that just having, again, relatively simple basic understanding of mechanics and energetics really leads to really testable and hypotheses that are likely to be confirmed. Really, all the work that you've done really in this area really is really based on relatively simple concepts in the end, and it really, as you said, it really works. And that's really a key. That ties the education to reality. And my question for you is, with regard to your experiment, so you have the smart pump, which is regulating regulating RPMs. How did you, in the control arm, how did you set the RPMs with a fixed? So, and that links with the question, which is, let's say clinically, wouldn't I want to just run the RPMs as high as possible so that I don't get suction or arrhythmias, and just leave it at the maximal speed? So how did you set the RPMs for the control group? And how would the smart pump have an advantage over just setting the RPMs at the highest possible value that I could?
Well, in our case, we are using relatively small animal. And the pump we are using is CP. So they are capable of sucking the heart. So highest flow is not an option. So we have to control a particular value, and for the purpose of controlling to a target value, basically we are applying almost PID type of regulation. But the real problem is that the system being controlled keep changing. So the system being controlled is not necessarily LV Impella combined system. Under some certain condition, it can come with left atrium, pulmonary venous system are also included in those mechanical systems. So that's why I need to identify the system first and allow pretty much variations in those systems. Then we design the feedback regulator. So that part was one of the most difficult part of this project. But once you established, then the standard, conceptual standard PID regulator works beautifully. That's what it is.
Okay. Yes.
I congratulate you to this work. I believe it's very important because responding to this question, if you just run the pump at highest level without running into suction clinically, this is really challenging because conditions are changing all the time. If you're running near the full level, you get alarms, suction alarms, with the CP, for example, very quickly, which decrease the acceptance by the personnel and the resistance by the level. So having a system that finds the optimal work point also from the clinical side is a huge progress in my view.
Okay, so with that, we will continue. Kenji, thank you very, very much.
Thank you.